Hello everyone. In this video, I want to talk about the steps of GD&T as a summary, basically, because we have seen it in a bunch of previous videos, and go through it with an example. So there are three major steps in GD&T. Step one is you select the datum features and refer to them with these leaders. And most of the time we need three datums: primary, secondary, and tertiary. And as I talked in previous videos, which surfaces, which features do we choose as datums? The one that are involved in assembly. Which one do we typically take as primary? The one that is typically a bigger surface and more stable. Okay, so that is about selecting datums. Then we have to qualify these datums since they are the base and the object is basically stabilized on these surfaces, so they need to have some qualifications before we look at other features. And most of the time we typically have our primary datum, especially if it's a surface, to be what? To be flat. If it's an axis, we typically try to control it with dimensions or maybe with the straightness. And then secondary, if it's a surface, we try to make it perpendicular to primary. Or if it's an axis, also we can make it perpendicular to primary. And then tertiary, we might make it perpendicular to a primary and secondary. Or if it's a feature of size, we might use a position for that or something like that, right? But most of the time, a combination of flatness and two perpendicularities for many of the surfaces would work, again, depending on what those surfaces are and how they are used in assembly. This is very common. And finally, now we go to the features. Any surface, any feature other than the datums, now you try to basically provide geometric tolerance for them. If they are a feature of size, use a position for them. If they are just a surface with no dimensions, use a profile for them. Okay, so these are the major steps of GD&T. So now a few things that we need to talk about along with the example. One is the flatness and the perpendicularity that we use for these datums. The tolerance region for them, the tolerance zone for them, are on one side of the truth surface. But for position and the profile, these two, they are on both sides of the true feature, okay? So they are symmetric, while perpendicularity and flatness are not. And that you can see in this example here, where datum A here is the back surface, and we asked it to be flat with 5 thous. And then B here is what is the bottom surface that is perpendicular to A with, again, 5 thous, and C again is the left surface perpendicular to both A and B with 5 thous. Okay, so the surfaces are back, bottom, and left, and you can see that the back surface is the biggest surface, then it's the bottom surface, then it's the left surface. That's how we chose primary, secondary, and tertiary. And the reason we chose them is because this object has contact with all of those three surfaces, okay? So this object has a contact here with the object it is assembled to. It has a contact here, and it's also sitting with the back surface on that object, okay? So this is the first and the second step is to identify your datums and qualify them, okay? So here we've gone through steps 1 and 2. And the important thing I mentioned is if you look at the tolerance zone for flatness, you see this is this red area, and it is on one side of the true datum A, okay? So datum A is this back line, and you see it's only on one side of it. So the thickness of this region is 5 thou. And also perpendicularity here, if you look at this again, you see for the bottom surface B, again, it's on one side of this true surface B. And also for C, again, it's on one side of true surface C. Okay, so perpendicularity and flatness are on one side of the true datum. Okay, but profile and position are not. If you can see here, the feature we are talking about, the axis, and I'll show you when we talk here about this position, right? And we have a value of 10,000. You see here that the tolerance zone is a cylindrical region around the center with a diameter of what? 10,000. So 5,000 of that is on the right, 5,000 of that is on the left, as you can see. And the same thing for these other two holes, right? You see this 0.12 that we have for these two. Again, you see that's the diameter of these circles. Okay, so it's symmetric about the center. And also the profile that we're going to use with the thickness of 20,000, you can see that thickness 20,000 is on both sides of the true surface. So if this is the true surface, then 10,000 is on one side of it, and 10,000 is what? On the other side, and the thickness of the whole thing is 20,000. Okay, so keep that in mind. So now, as I just showed you, we need to go and what? We need to go and talk about the features, right? We need to talk about the features, and what features do we have to talk about them? Well, the back surface, the bottom surface, and the left surface are completely qualified because they are datums and we have qualifications for them. What we need to do is, the first one is probably this big hole here, and that big hole is a feature of size. You can see it has a diameter. So for that we have to use what? As we said, we have to use position, and that's exactly what we are doing here. We are using a position. And of course, we need all three datums for that. We need to fix the part completely before we measure the position accuracy for the center of the drilled hole. And here, there are two things that we need to talk about. One is, phi means it's a cylindrical region, okay? The two things we need to talk about is, one is the size of this region. The other one is why is it that we used MMC here? And by the way, the same thing applies to these other two holes. If you look at these two other holes, which are our next features, again, they are feature of size. So we use position for them, again, with three datums in place. They are cylindrical regions, the tolerance zones. So again, how did we pick up this number? Why did we use MMC here? Okay, so let's talk about that before we move on to anything else. Right, so that's the next question: how to determine the size of tolerance zone for the holes, and do we use MMC, LMC, regardless of feature size or what? So first of all, why do we use MMC? MMC is used when you have what? When you have clearance holes. Okay, so whenever you have clearance holes, you try to use MMC, right? So if the hole is made a little bit bigger, the center of it gains some bonus tolerance and can be off a little bit more, because the bigness, the largeness of the hole will compensate for that, right? If I have a bigger hole here instead of this, even if it's a little bit more off, then because it's big, still the pin that is going to go into it can probably go into it. Okay, so because it's a clearance hole, I use MMC for them. So here the assumption is all of these three holes are clearance holes, and the pins that go into them should freely be able to go in and out without any force or anything. Okay, if they were not clearance holes, if there was a bushing here or there was a press fit or something, then we do not use MMC. So please pay attention. If these holes were not clearance holes, we will not use MMC, because we do not want to allow basically for any bonus tolerance. Okay, we want to keep everything in good shape and make sure that we don't allow bonus extra deviations, extra tolerance, bonus tolerance. So we still can put the pins in. So if it's a press fit, we typically use a regardless of feature size, which means not put anything there, no modifier. Okay, if you don't put any modifier, it is regardless of feature size, which I mentioned in previous videos. And sometimes we might even use what? The LMC. Okay, so clearly for a non-clearance hole, interference hole, or anything like that, we would never use MMC. Okay, now the question is, where would you get this number from? 10 tau, where does it come from? Well, a simple typical thing for it is here, to get that number, we look at what? We look at the smallest size that the hole can have, in this case 0.75, right? And then we look at the size of the pin that needs to go inside this hole. And for that, okay, we look at the maximum diameter of that. So let's say in this case, this is like 0.74 and maybe 0.72, something like that. Okay, so we look at what? We look at the MMC of the shaft, and we look at the MMC of the hole. And the difference between these two numbers is going to be the allowable tolerance zone for the position. Okay, so for a clearance hole, the position tolerance is typically what? The MMC of the hole minus the MMC of what? The corresponding pin. That's how we got that. For instance, in this case is probably what? If you look, the minimum diameter is what? 0.342, right, for the hole. And here, this much position tolerance means that the MMC for the shaft was how much? It was this number subtracted from that, so it was 0.330. And this guy was what? This was the MMC of the hole. Okay? So this is how you determine the size of those position tolerances. Okay, so what else is remaining? Now that I got all of my surfaces, or most of them, basically qualified, is there anything else left? Yes. What is it? Well, I took care of this, 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 and the back surface entirely. So the only thing remaining, as you can clearly see, is what? It's basically this area. Here, here, and here, huh? This green area is all I have left to take care of. Once I take care of the green region, it's almost done. And how can I do that? Well, this whole green region is not a region with a single dimension or something. It's an entire surface. And since it's a surface, for it, I use a what? I use a profile. And since it's not the entire surface, it's only a portion of the surface, I'm not going to what? I'm not going to use an all-around symbol here, because if I do, it means all of it. But I don't need all of it. Why? Because this portion of it in red and this portion in red, they are datums, and they are already basically qualified. So here, I only need a portion of it. Therefore, between the beginning of it, I use a leader X, right? I use a text, say this is point X. The end of it, I use Y, and here I say what? In my the profile, I say between X and Y, okay? And the size of this region, which is also symmetric, that depends on what? Depends on basically the if this one sits against something, and it's fit inside of it. So let's say this part that you have like this, okay, this part that you have like this, when it goes into something to sit against it, right? So let's say this is the mating part that you have, right? Maybe like this. So it depends on how much room you have, okay? Depends on what are these sizes here. So if you look at, for example, this size from here to here, what is it going to be made at the smallest, right? What is it going to be made at the smallest? And then you have your basic dimension here, which you can see, for example, here you have 1.2, right? And then here you're allowing for what? You're allowing for, as I said, 0.1 above and 0.1 below it. So it's 0.2. And the same thing here, 0.1 above it and 0.1 below it. So if this is a 0.1 and this is a 0.1 and this guy is 1.2, probably the basic dimension you have on the mating part is something like 1.4. Okay, so you choose these to make sure that this profile sits in the mating part and there is no problem over there. Okay. So these are some basic calculations and simple scenarios, and the examples could get a lot harder than this. In future videos, I probably go over harder examples. But here, with a simple example, I wanted to show you how to start the GD&T by creating the frames, qualifying them, and then whatever feature remaining, use a combination of position and profile and qualify them for, or not qualify them, I mean tolerance them, and make sure that you have not missed anything. And here you might say, well, what about this chamfer here? Well, chamfer is not probably as critical, but does it include anything? Does this chamfer have any tolerance or anything? The answer is yes. Most of the time, right next to our GD&T, we typically use a general tolerance note and say, hey, dimensions are in mils. Unless otherwise specified, the dimensions are basic. When you say that, then you don't even need to put this 1.5 in a box. If here you simply said this guy is 1.5, and you did not even put it in a box, it's absolutely fine, because here you mentioned that they are what? They are basic, and then you say any surface that I did not mention, they are all what? They all follow a profile with respect to ABC with 0.5. So in this case, this chamfer also will have a what? Will have its own region, right? This chamfer will have its own region. Let me use a thinner thing, maybe this one. So it is going to have its own tolerance zone like this, where this thickness from here to here is what? 0.5. Okay, that will be for the chamfer or anything else if we miss them. So you always put a general tolerance node next to your GD&T to make sure everything is covered. And this is typically a looser tolerance for the stuff that are not as important yet might not be mentioned in all of these symbols. Okay, so the ones that are very critical and important, you definitely want to make sure you have something for them. Okay, and the more critical they are, the smaller chance they have for error, room for error. You make sure you choose these tolerance zones what? Tighter. Of course, how tight? It depends on your machines, and it depends on how much cost you want to consider for the part, because tighter tolerance always means exponentially higher time and cost of manufacturing and inspection. So hopefully the video was useful to you, and I'll see you in the next lecture. Thank you.